halogens are all poisonous. Bromine especially is a carcinogen. Okay, it causes cancer. The halogens, there's a table 3.6. In general, if you go and have a look at melting point, fluorine is a gas, iodine is a solid. So what happens to melting point? Does it decrease or increase down a group? It increases, because solids have higher melting and boiling points than what gases do. All right? So general tendency, melting point increases. Boiling point also tends to increase down the group. The state at room temperature, fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid. You must know that. And their colors, yellow, green, brown, and purplish, or almost black. The group 7 compounds, they are very reactive, and they like reacting with the metals. Okay? So they form ionic compounds. And when they react with other non-metals, for example, hydrogen chloride, it forms covalent bonds. No, it forms molecular substances. Hydrogen sulfide, carbon dioxide, sulfur dioxide. These are molecular compounds, and molecular compounds have low melting and boiling points. No, they are usually in the form of gases. Single ones of them will be a solid at room temperature, and usually they also undergo sublimation if they are solids. More about the group 7 elements. They form ionic compounds. Metals are hard. They are crystalline. They contain negative ions. Typical one is sodium chloride. We talk about the halogens, and their ions are the halides. But I've repeated that so many times, you should know that by now. An anion. The halogens. Fluoride, chloride, bromide, iodide. Yeah, they're all -1. They all gain 1 electron when they form ions, because they have 7 electrons in their outer shell. Most halides are soluble. Here's one of the solubility rules that you can go and learn. Fluorine, chlorine, bromine, iodine, they are all, their compounds are soluble, except silver, lead, and mercury. So mercury chloride is going to be a solid. Lead fluoride will be a solid. Okay, but all of the other salts, when they combine with the metals, and they can combine with a variety of them because they are very reactive, they will all be soluble. No? So all the halides are soluble except silver, lead, and mercury. Okay. What more? All right, that's the halides. Okay, done. Top of page 45 there, they say some halides are insoluble ones. The ones that are insoluble are silver, lead, and mercury. In general, when we test for the presence of halide ions, in other words, we don't work with fluorine that much either. Chlorine, bromine, and iodine. When we test for the presence of this in a solution, let's say I have a test tube, and in the test tube I have a little bit of potassium iodide. All right? Now, how do I go and identify the presence of chloride, bromide, or iodide? So what we go and add in with all of them, we usually add a little bit of nitric acid. That's the first step. The nitric acid simply functions to, if there are any insoluble contaminants possibly in the solution, it keeps it in solution. Then the reagent with which we test for the presence of halide ions is silver nitrate. Now, you could have actually tested with lead nitrate or mercury nitrate as well. Okay? Because they will all form insoluble salts. But I think some of the others under special conditions will dissolve. So the reagent we use to test for group 7 elements is silver nitrate. Silver nitrate looks like water. All right, if you mess it on your skin, it changes your skin dark brown. It's like it reacts with the proteins in your skin. Okay. No, I think they're fairly neutral, the salt. Yeah. No, not at all. No. Okay, now what happens is, let's say I have a solution of potassium iodide and I go and add silver nitrate. We are going to get silver iodide and potassium nitrate. So we get silver iodide, and this thing is insoluble, plus potassium nitrate, and all nitrates are soluble. So this stuff will form a precipitate. Now when you do this test, well, they differentiate. They say that this one, silver chloride, they say is white. Silver bromide is cream. And silver iodide is yellow. This is the precipitate that they're talking about. Now, unfortunately, the white, the cream, and the yellow precipitate, their colors are so close together that you could maybe guess the one that is white. But if you have a precipitate, a single test tube, you cannot decide whether it is cream or yellow. So we have to go one step further to go and confirm. We now know if you get this white or cream or yellow precipitate, we know we've got one of the halides. All right? But which one? So the second part of this test is we start with dilute ammonia. Now, ammonia, when I dissolve it in water, it forms ammonium hydroxide. Okay, so I go and add dilute ammonia to my first test tube. If it is a chloride, that white precipitate becomes soluble. It disappears and you get a clear liquid. Okay. If you go and add dilute ammonia to that one and that one, the precipitate stays. So now you have separated the chloride. The next step, yes, they will be insoluble in dilute ammonia. The second step is to use concentrated ammonia. Now, when you do the test, obviously this one will become soluble because it's soluble in dilute ammonia. But you will find that this one becomes soluble in concentrated ammonia, soluble in dilute ammonia. Yes, you do it in steps. And then you will find that this last one remains insoluble. And then you have distinguished them from each other. Dilute ammonia. Do you understand? This is very important work. Okay? You need to know this. The identification of the halide ions in your textbooks. No, we don't work with that. Your syllabus just specifies chlorine, bromine, and iodine. Okay. The test for halides in your textbooks, page 45, they say the reactions of halides with silver nitrate solution, followed by some dilute ammonium hydroxide, is the standard way of distinguishing between them. In the table, they show clearly chloride is a white precipitate, bromide is a cream, iodine is a yellow precipitate. Fluoride doesn't form a precipitate. There's a different way to test for that. It's not part of your syllabus. Then they say with dilute ammonia, the precipitate, the chloride, dissolves. The other two remain insoluble. So how do we distinguish them? We use concentrated ammonia, and we will find that the bromide will become soluble and the iodide will remain insoluble. Okay, that's it. Yes.
This broadcast is made possible by the Capricorn Group.
Wow, what a run! Yunmin Son from inside his own half has scored! Staggering! Just staggering! Drama from day one! Messi tries a shot! Leo Messi celebrates that one! This is the league we want to watch! Where does football go from here?
Live sport is coming back. Reconnect to DSTV and get an upgrade on us.
Share with us on #LearnOn1. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
Period, we had a look at the test for chloride, bromide, and iodide. Just to recap very shortly, because this is very important, we add silver nitrate. In each of them, we get a white precipitate, a cream precipitate, and a yellow. But you saw that they are very difficult to distinguish. One would probably, if you took a guess, be able to guess the white one. So there is a second step that we do to this test. We go and add dilute ammonia. It's just NH4OH, all right? Dilute ammonia, and we find that this one will dissolve, the rest will stay. Then we take concentrated ammonia, and that one will dissolve, but that one won't. All right, this is an important test. Over here, they acidify with a bit of nitric acid, just for impurities that could possibly interfere with the test. Okay. Now, we are still busy with the halogens and the halide ions. The next thing is the reactivity of the group 7 elements. I have said to you, fluorine is the most reactive, iodine the least. Okay. Now, they can undergo displacement reactions. And the rule says the more reactive halogen can displace the less reactive halide from its compound. All right, now what does this mean in practice? For example, let's take fluorine, because fluorine is the most reactive one. So if I have fluorine and I have a solution, for example, of potassium iodide, we will find, if you go and look at the reactivity between fluorine and iodine, we will see fluorine is more reactive. So according to this, the more reactive halogen, that one, can displace that one, the halide. So the product that we will get would be potassium fluoride plus iodine. Yes. Okay. It's an easy one. So, what it comes down to is fluorine gas can displace chlorine from potassium chloride, bromine from potassium bromide, iodine from potassium iodide. But chlorine cannot displace fluorine from its compound. In other words, if I gave you this equation, if we said we have chlorine there and I bubble chlorine through a potassium fluoride solution, what is going to happen? Which one is more reactive? This one or that one? That one is more reactive. So can the less reactive one displace the more reactive? No, it can't. So here won't be any reaction. Yes. You say no reaction. Okay. Yes, you need to know them. All right. That is very important. So this is, yeah?
So with the non-metals over there, the reactivity increases the way you go down.
Not all of them, but specifically group 7 decreases as you go down. Okay? It depends on from group to group. Okay. So in your textbooks, they're on page 46. Oh, okay. On page 46, we have the displacement reaction. They say it starts right down at the bottom of page 45. They say this reactivity shows the reaction between halogens and other halide ions. It shows that when a halogen high in the group, in other words, a reactive halogen, containing the, is added to a solution containing the ions of one lower down, in other words, less reactive, there is a reaction. For example, chlorine solution is added to sodium iodide. There's a reaction. Chlorine plus sodium iodide will give you sodium chloride plus iodine. Below it they say, this is because the chlorine is more reactive than the iodine. It competes with the iodine for the sodium ions and wins. If bromine solution is added to a solution of sodium chloride, there will be no reaction because bromine is less reactive than the chlorine. Mark off on that same page, question 3.5, 3.6. And, okay, not 3.7, 3.5 and 3.6. The next group that we look at is the group 8 elements, the inert or noble gases. Why are they inert? Why do we call them noble gases? They have filled outer shells. What does this mean? They don't have bonding places, so they can't bond. Now, it's not impossible. One can force them to react, okay? But in general, for the extent of our syllabus, they do not react. High temperature, high pressure, catalysts, etc. But it doesn't go easily. Okay. So, right at the bottom, page 46, the unreactivity of the inert gases is that they have a full shell of electrons. And then there's a table, 3.9, general properties. We find that melting and boiling points and densities increase as we go down. All right. Melting and boiling point and density increases. Some of the uses of the inert gases everywhere where we need an inert atmosphere, for example, in light bulbs. They say the helium is used for filling airships and balloons. Now, historically, they used hydrogen as well. What was the problem with the hydrogen? Yes, it makes an explosive mixture when it's mixed with oxygen. All right, so the airships from the olden days, they used to be filled with hydrogen, but nowadays if you want to have an airship, it will be filled with helium, because helium is unreactive. They say it fills airships. It's used mixed with oxygen to form a gas for divers to breathe. Why? Yes, because the other elements can react. Okay? We are not designed to breathe pure oxygen. We breathe approximately 1/5 of the air that you take in contains oxygen. So when you go deep sea diving, can you suddenly start breathing pure oxygen? No. So they mix it with helium. Why with helium? It's unreactive. All right, because some of the... It's probably got to do with the availability, yes. Okay. Neon used in fluorescent lights. When an electric current is passed through neon, it gives off a bright light. Argon, filling of light bulbs. It's unreactive, so the filament does not burn away. The next group that we have to have a look at is the transition metals. Now remember we said that in terms of the properties of metals, shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. But how do they differ from the group 1 and 2 metals? Usually the transition metals have high melting and boiling points, higher densities, and they form colored compounds. While the group 1 and 2 metals have lower densities, lower melting and boiling points, and tend to form white salts or compounds. Table 3.11, just general properties of some of the metals. There isn't a pattern that you say it decreases from left to right or from top to bottom or increases as you go. It's just very general. They've listed scandium, titanium, vanadium. So scandium, titanium, vanadium, then chromium, manganese, iron. It is the first horizontal row of the transition elements. It's period 1, 2, 3, 4. No? Okay? Iron, cobalt, nickel, copper, and zinc. So they've just taken the first row, horizontal row. And very simply, if you go and look at melting point, it tends to decrease. Boiling point tends to decrease. And density tends to increase, although there are some discrepancies. All right. They like asking questions. They give you a list of melting and boiling points, and they say, describe the trend. Then you must go and see, is there a general increase or decrease? Yes or no? It increases or it decreases. Are there any aberrations in that list, with the exception of that one and that one? Okay, that's how you describe the trend. Yes, you don't need to remember specific values or give specific reasons on that one. Okay. On page 48, if you go down, the first sentence below the table, these metals are much more dense. And in the second paragraph, transition metals form colored compounds. And then they list a couple of the transition metal salts, and you will see they are yellow, purple, green, blue, orange, brown, red, etc. Okay, they form colored compounds. It's not that some of them don't form white salts. For example, zinc forms a white salt, okay? But in general, they form colored compounds. In general, the transition metals are also very often used as catalysts during industrial processes. And one of the topics that we will have a look at a little bit later on is some of these industrial processes. Okay, so the catalysts then are probably transition metal elements. Uses of transition metals, because they are hard and strong, and because they are fairly unreactive in comparison, for example, to sodium and potassium and magnesium. All right? Iron doesn't start burning if you make it hot enough, but magnesium does. So relatively speaking, because of its unreactivity, strength, hardness, etc., these metals are used in industrial processes and in manufacturing when we need, for example, tools, etc. So they say transition elements are hard and strong, and they are not easily corroded. So one important use is as a catalyst. We've just done that. What does a catalyst do? How does it work? Yes, you know the little rhyme. Catalysts make reactions go faster because it lowers the activation energy needed. Okay. Table 3.13. There they're going to have a look at some industrial processes. We will have a look at ammonia, sulfuric acid, the making of those two. The catalysts are iron and vanadium and platinum and nickel and titanium. Making of polythene. You must just know one or two uses. The first two, definitely, iron and vanadium, because we are going to do the Haber process and the contact process. Iron is in the manufacture of ammonia, the catalyst, and in the manufacturing of sulfuric acid, the catalyst is vanadium. Okay, I think I must stop at this point, because the next thing that we must do is the transition metal ion, the complex ions. Okay, and it's slightly different from what you've done normally. I want the whole period, because we're just going to get started and we're done on that. So at this point, I am going to stop. Yes.
Love to hear from you. Send us your views, comments, and videos with your name and town to the One Africa TV's WhatsApp on 081-200-6659 or send an SMS to 555. One Africa TV. It just gets better.
My dreams with the creators of the universe in this part of the world that we living in. Surrounded by mountains, looking for the millions, go for the land that they promised me. Dilute City, my favorite city, I got it on my back, Timbuktu. Dilute City, my favorite city, I'm looking for the millions. Dilute City, my favorite city, I got my back, Timbuktu. Dilute City, my favorite city, I'm looking for the millions. I got my back. They're looking for the talent, but they overlook the talent. The talent on the streets, but they're scared of the streets. What if I beat it like Michael Jackson? What if I run it like Frankie Fredericks? Run it, I'ma run it, I'ma get it. When I get it, I'ma spend it, I'ma leave it with my lady. They gon' get it, baby, get it. My dreams with the creators of the universe in this part of the world that we living in. Surrounded by mountains, looking for the millions, go for the land that they promised me. Dilute City, my favorite city, I got it on my back, Timbuktu. Dilute City, my favorite city, looking for the millions. Dilute City, my favorite city, I got my back, Timbuktu. Dilute City, my favorite city, I'm looking for the millions. Favorite city, I got my back, Timbuktu.
I know to the bed. Microphone checks and 212s. Let me meditate. With every single step I make my move. Ooh. Natupandule. Elephants just walked in the room. True. So my heavyweight. Uno nabaju up in the place. So tuno kumono bongo on a regular. So the tambulo mambo tambulo cellular. Uno bukala wa kinja kala nyilalua. These bright lights are to blame for these nights and the fame.
Living in the city, working for my village. I'm drawing the landscape of my dreams with the creators of the universe.